which produced Robot Foundation's models analysis behind today's talk. So everyone, please welcome Sebastian.
Good afternoon. As mentioned, Neil is unfortunately sick. That's why I'm stepping in. But today, I'm going to talk about how scaling has been transforming AI and to what extent this also applies to robotics. And we should expect transformative changes in robotics over the next couple of months and years. So let's start with the dream of a general purpose robot system. You all probably have tasks, either at home or at work in manufacturing context, that you would love to have automated with, So let's, for instance, at the home settings, I guess most people don't like to clean a toilet, or they don't like to remove the weeds in the garden. But the reality so far, or today, looks closer to lawn mowing robots that bump into like the corners of like the garden, or like in industrial settings, we have robots that repeatedly always do the same kind of sequence of tasks. And have very little generalization capabilities. And we call this paradox Moravec's paradox. It goes back more than 40 years ago by Hans Moravec, who basically said, well, robots excel at tasks that are highly structured and in structured environments and rule-based, but they are kind of impossible, or like they struggle in environments that are unstructured and require some kind of reasoning. Also, you have probably seen a lot of demonstrations on robots recently, specifically like on social media, robots doing, for instance, backflips. Those are probably tasks that are fairly impressive, because like I would assume many of us probably can't do this, at least I can't. But at the same time, those systems follow some kind of rules, and they can do things and outperform even the best human beings. But on the other side, they struggle with, for instance, just putting a USB stick into a computer that is fairly intuitive for us, but very hard for a robot to do. And this also applies to all the other pack and hold tasks that you see in manufacturing context. So in the physical world, we have systems that can work well with rules, but very bad with if it's like unstructured. Also in the digital world, until very recently, we had always like our automation pipelines have been based on rules. So for instance, take the customer support systems. Like if we, for instance, used to call customer support of a given firm, we always had some kind of option menu that we could press with some numbers, what we wanted to do. And like until very recently, this was also, from a customer experience perspective, not very pleasant. But like with LLMs and also other foundation models that interact with us, for instance, voice, allow us as well to have this kind of natural user interface. And now the big question is, well, will robots get there too? And if they do, what is the impact for the economy? Is it larger than LLMs? Is it slower or smaller? Or is it on par? And Neil and I, and generally like the FutureTech lab, we are very interested in studying this. And one line of research is this, basically, where we looked at, well, what is the exposure of LLMs and robotics across the industry for different job families? And you see, well, the exposure is fairly high. And I'm going to say, like, this doesn't mean everything is going to be automated in a second. But like, you also see the kind of tasks that we can automate with LLMs are vastly different from the tasks robots can do. I already mentioned this a little bit. This chart only presents like what in theory could be automated based on, it's about 20,000 different tasks that have been analyzed here across 900 different occupations. And what it doesn't say or doesn't show yet is, but that's also what we are interested in finding out, what is like the technical feasibility of those systems? How much does this shrink each bar? What is like, how many of those tasks are like economically attractive to automate in the sense of like the cost for training those models and deploying, but also like the integration in like, for instance, the existing workflows is lower than, let's say, the gain is higher than the cost by itself, but also it does not consider, for instance, regulatory conditions that might go in hand with that. Okay, so I just mentioned for the physical world, we are still kind of rule-based. We are not really like agnostic, and we can generalize across tasks the way we would like to have it. But like for AI in the digital world, we have been able to do this with ChatGPT most famously. So now the question is, why do we have ChatGPT like 3.5 years ago, and not, for instance, already 20 years earlier than that. And there's 3 reasons for that. The first one is, well, we didn't have the internet, or like the internet was still in the early stages, so we didn't have the amount of data that is used to train those models. We didn't have the smartphones, we didn't have social media back then, so we just didn't have the data. The second one, we just didn't have as well the understanding and the knowledge how our algorithms should process this kind of knowledge and handle as well. There's like tools, but also like the transformer that is widely accepted or like fairly known are like examples for this. And the third dimension is also our computers back there were simply not powerful enough. We didn't have enough chips to basically build data centers in the size of data centers today, and we didn't have each individual chip was also not powerful enough for like memory capacity, for instance. And maybe a fun fact, as far as I know, NVIDIA released their first GPU just in 1999, so also not that much earlier than that. Okay, so now over time, as we have more data and as well like more compute, we have been able to use more of those resources and make our models bigger. And this is basically charts that like Epoch AI has been creating, where you see very nicely that there's like an upward trend line. And also this basically shows very nicely the difference between, for instance, GPT-1 from 2018, I believe, and GPT-3, that was ChatGPT in a sense, and as well like the state-of-the-art frontier models. Okay. We can do, but also there's one reason why we'd look like to scale it up, and that's basically because of the scaling laws that I'm going to talk today about. And the idea of the scaling laws is as well that the performance gets much better as you scale up the resources. And this is one very nice illustration with the kangaroo, or like I'm going to read it out, the prompt. So a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends." And you can see here on the very left that the model with only 350 million parameters, it doesn't really look like a kangaroo. It doesn't really look like the Sydney Opera House. It doesn't really look like "Welcome, friends" on the board. But if you scale up the model size, like to, let's say, 20 billion, well, this looks like a kangaroo. Yes, it does look like the Sydney Opera House we all know from as well images. And yes, it also the writing seems like there's no typo in, right? So this is impressive. And also for compute, this is super important and super interesting. What we see that like over time, the amount of compute, just like the amount of like chips, hardware quantities, has been scaled massively. At the same time also, we see that those chips have become more efficient. So we could like use more of those matrix multiplications with the same resources. And additionally, that's also super interesting that like the lab has been working on is the algorithmic efficiency that we have of those systems. And maybe to put some number to this, so to reach the same level of performance, we only need, or like we can actually halve the compute required every 8 months, which is pretty impressive if you look at like how much computation is going into these large language models. Okay, I already touched on like the importance of scale here. And one more thing that is super important is like the term known as neural scaling laws. So there is an empirically predictable relationship between those input resources, compute, data, the size of a model measured in parameters, and how well those models perform. So, and it's surprisingly simple. It's just a power law. And with that, we can actually predict how well a future model will be given the input resources, but we can also estimate what is like the amount of data that we, for instance, need to reach certain performance thresholds. And then also, well, those models are fairly expensive. We are talking about hundreds of millions today for AI. Well, we also want to have it efficient, and also those kind of estimations or like scaling laws help us estimate like what is the perfect relationship between, for instance, the amount of data and parameters as well. And also maybe I should mention those factors are not by itself, but also linked to each other. And from a practical perspective, it's super important to point out that you have diminishing returns with scale. I'm gonna as well touch on this in a second, but it basically means that like you need exponentially more resources to further improve those systems. And it's also super task and modality dependent. Okay, so this is how basically since 2020, since we have the insight that like those scaling laws exist, like we have been, or like all the frontier AI labs have been scaling up the system. And this is like the #1 reason why the systems perform better. Okay, I now talked quite a bit about AI, but I guess I'm here because it's robotics time. So why do we have, let's say, general purpose chatbot systems, but we don't have the general purpose robot, despite the fact that the term robot is about 36 years older than AI. So it's 1920 versus 1956. And well, this goes back to robotics is a little bit harder than AI. Well, there's like the real world complexity in the sense of, well, if you take a string of text, it's one-dimensional. If you take an image, it's two-dimensional. State-of-the-art humanoid robots, they have about 70 degrees of freedom. And maybe just for your own understanding and knowledge or fun fact, like humans have about 200 degrees of freedom, basically, like in every joint and link. Additionally, like robots typically, or like oftentimes, operate in dynamic environments that are also super unpredictable. Then we need to take into consideration like all the physics that we play as well in hand. Like no one has really like gravity, friction, contact forces. Those are hard to model as well that apply to robotics, but like they don't apply to, let's say, LLMs. Then tasks are fairly long. If you give like a prompt, hey, please clean up the kitchen, this can be rather long and is not like done within 5 seconds. And also for the amount of data that is needed, well, we can't use, let's say, 100 robots and use reinforcement learning through trial and error, figure out what works and what doesn't. Well, that's going to break a lot of robots. And this also brings me to the next talking point, the role of data here. So robotics is heavily data constrained. So we don't have an internet scale, or like we don't have an internet for robotics data. Also, let's say the collection is harder. If we do like the teleoperation, for instance, we need to do this manually. This requires a lot of humans, a lot of hours doing basically all over the place. And we need to show a robot, for instance, how to fold laundry or how to make a coffee, or as well like in manufacturing settings as well, how to put a screw inside or like for assembly. And the last thing as well, just like the information richness between those modalities differs as well. So you can imagine like if you have a video which consists of multiple frames, and like if you have a camera with 30 hertz, that means like the change between each frame is very low. So basically like you have a very low information gain between frames. At the same time as well, like the information difference between neighboring pixels in an image is also fairly low, meaning that like, so Neil and I did this estimation, we assume that we have about 1% of the same comparable rich data in robotics as we have for LLMs. That's a big difference. Also assuming that like we need to collect this manually. Okay, so Neil and I looked into whether to what extent scaling could actually solve this. And the short answer is yes, but it also might have its limits. So we do find the same power laws that we also find across all the other modalities. And more specifically, like this not only applies to language, but also to vision, biology, physics, math, coding, like across the board. But this also means we will have diminishing returns. So to get the models increasingly better, we need exponentially more resources. And how this looks like, I'm going to show you in the next picture. So this is how you can imagine the power law to look like, with like the success rate on the x-axis and the cost, like here measured in like the amount of like how much more data you need, shown on the y-axis. And you see, to get from 0% success rate to about 70%, you get 100 times, or like you need 100 times more data. So like, let's say 100 demonstrations. Well, showing a robot how to do a certain task 100 times, this takes probably like a couple of hours, that's doable. But like, if you now think of your manufacturing settings, 70% is probably not enough. You want to get something closer to like 90% plus, typically, right? And you can see that like the cost of getting there is increasingly, and also like is pretty enormous. So that's the question where as well things will get very expensive, and we will see how this will play out. Additionally, it's very interesting that, and this is maybe hope for us, is that if you look at the efficiency between modalities, so doubling the performance of a language model, you need, for instance, about 2 million times compute increase to double the performance. For a 64-pixel image, it's about 40 times compute. That's a big difference. For robotics, we are a little bit more efficient than LLMs, which gives us hope that we will have measurable progress as well over the next couple of months and years. Also, it's super noteworthy. Some tasks are more complex than others. We do see a difference there, so there's a wide spread. And also, the general performance in the studies that we looked at is fairly low. So like the mean top performance of one of those scaling laws that we looked at was 67%, so it's not super high. But also, as pointed out, like typically we are in the low data regime. So to summarize this, we're in the very early stages of scaling up those systems. We do have some understanding of how those systems work, but there's like a lot of research that we still need to do, both on the technical side, but also then later on the economic side, on where it basically is most attractive to automate, for instance. So the open questions that we have is the first, well, how far can scaling by itself bring us? Or do we need as well, so for instance, some kind of additional engineering and as well advanced, let's say, integration systems that will help us with the automation? The next one is, well, how do we collect the vast amount of data? How long will this take us? Which will give us the outlook of like when we can as well assume to have these capabilities come up in industry, but also like in settings. What will it cost us? And will it as well be, like from an economics perspective, be lucrative to use these tools? And the last one as well, which tasks should we prioritize data collection for and also automating? And which ones are maybe like infeasible from an economics perspective to automate? And then also in a broader sense, what does this mean for society in terms of productivity and the economy with like labor market implications? I would like to finish with one more chart, simply because there's a lot of hype. You always see fancy demonstrations of things that can happen, but we also, in our lab, we often see like automation does not only mean it's going to be automated right away. In a sense, you can imagine your own job. Like, for instance, if you use a computer, well, there's like many dimensions to it. Well, it's one opening a computer, then maybe it's pressing a button, typing, maybe putting a USB stick in it. But then also there's some task involved with reading, for instance, emails. There's task with, for instance, making some kind of decision making. So you see there's like a wide range of different tasks that your job consists of. Now, if you think of, well, how many of those tasks really be exposed to a robot, for instance, it's typically those, let's say, where you put in a USB stick or you put it on. And you probably don't want to have a robot type your emails. You want to have the digital interface. You already see from all the tasks that you do, this will narrow it down. Now the next question is, well, how much of those tasks can be automated from a technical perspective? And this will shrink it again. And then if you think, well, it takes me one mouse click or something like this, it's probably not all interesting to automate this single step unless like the economics of scale come into play. So there's like a difference between what is technically feasible, what could in theory be automated, and also what this means for the economy. And with that, as a summary, so AI has been driven by scaling those systems, and robotics may follow similar dynamics. We don't know yet the timeline. There's a lot of resources going into this right now, and also we don't know exactly what the impact will mean. And at our lab, we are very interested in studying the technical progress, but also how the intelligence of those systems evolves and what this means for the society and the economy. And with that, thank you very much.
Thank you.